Hello, welcome back. The topic of this video is MRI, magnetic resonance imaging. This is a modality that relies on the nuclear properties of matter, so usually the hydrogen atom. And by reading out the magnetic spin of that atom, you can actually get information about tissues in the patient. And it's very good for looking at very subtle soft tissue contrast in the patient. So it's ridiculously ambitious for me to try to describe MRI in a short video, but I'm going to try. And I think if you understand the basics, that'll help provide a foundation. So bear with me on the first part of this. It's going to be quite fundamental and maybe a bit challenging to digest. And then as you get near the end, you'll see the applications and you'll see MRI images and how all the fundamentals play into that. So here we go, A to Z, MRI imaging. Hold on to your seat. Okay, so let's start with nucleus here. I'm going to draw it in blue. So this might be a hydrogen atom, for example. And I'm going to put it inside a magnetic field that points in this direction. Magnetic fields we label with the symbol B, and that describes the field strength. Might be, let's say, 1 Tesla field in an MRI unit. Now this nucleus has a certain magnetic moment. I'm going to draw like this with the arrow. So it's a magnet inside a magnetic field, and that in that case it precesses around. Here's what precession looks like in a cartoon, and you'll see it's basically spinning like a gyroscope around an axis in this magnetic field. As you increase the field, the spin increases. Okay, so the frequency of this thing spinning around in hertz, remember cycles per second, you can write an equation for that. It's gamma times B times the magnetic field divided by 2 pi. Okay, what is this gamma? This is called the gyromagnetic ratio, and it's a property of the nucleus that's in that field. Gamma you can write further as mu divided by I over h bar of Planck's constant. Mu is the dipole moment. I is the nuclear spin. Okay, and this has some values. So let's look at some examples. Most important one probably would be hydrogen. So it has a nuclear spin of 1/2. The dipole moment is given by this, 2.68 10 to the 7th hertz. And then if you multiply this out and you figure out what the frequency is, it is 42 megahertz per Tesla. That's a good number to remember. Another example, helium, spin of 0. So you can't do MRI with helium. Back to this picture. How do you use it to get a signal out? Here I'm going to draw a little coil in green. Like a kind of an electrical loop. You can have terminals coming out of it, and you can measure the voltage across those terminals. I can plot voltage, and it kind of will wiggle around as this thing spins. You're getting a voltage because anytime you change the magnetic field, that gives you a voltage through the wire loop. These voltages are what you measure. Okay, so let's go back to this picture. Drawing my nucleus again, it has some magnetic moment. Here I'm going to align it with the magnetic field. When you have that, the energy of this nucleus is given by this minus mu times B. It's negative. Now let me draw a nucleus that's oriented sideways, perpendicular. Here the energy is 0. It's basically just the dot product between the magnetic moment and the B field. And here it's anti-aligned. In that case, it actually has a higher energy, plus mu times B. Okay, so this is a low energy configuration, the ground state, let's say, and a high energy configuration where it's anti-aligned. You'd have to pump energy into it to get it into that state. And so that's what you can do. You can pump energy in, and that will take this nucleus and make it transition from the low energy state to the high energy state. What is that energy? Well, it's actually RF, radio frequency waves. If the frequency is exactly right, remember it's that Larmor frequency that we went over, then it will flip the spins from the low energy state to the high energy state. So here's what it looks like in a cartoon. RF wave comes in, the spin flips down, it put energy, and then it decays back towards its ground state where it's aligned. This decay rate here is T1 decay along the z-axis. And so here's how you would measure it in an actual coil that's placed on the patient. You'd measure the voltage, and here as the thing relaxes, it's spinning, you're getting this oscillating field. As it relaxes down, the voltage gets a little smaller, right? A little less magnitude, and so you can measure that over time. This is a signal that comes out of the MRI unit in raw data space. Now let's talk about how you would make an MRI image. A bit of history first. The first MRI images were made in 1977. I'm going to try to walk through this with a cartoon. So you put a patient and you align the magnetic field along this axis. It's a high field. It might be 1 Tesla or maybe even up to 3 Tesla or more. Let's take this example where at the middle of the patient, the field strength is 1 Tesla. Well, what you can do is actually put little coils in the scanner so that you make a little bit of an extra field over here at this end. And so here, and it's small. So here the field might be 1.0015 Tesla, let's say. Okay, then you can put a field over on this end pointing in the opposite direction with a coil, and then so it's a little bit, field's a little bit smaller here. Let's say it's 0.9, let's say 998 Tesla. Okay. Now what happens is the little magnets, the hydrogen nuclei in this region, spin a little bit faster than those in this region over here because the field strength is smaller. Remember, the frequency depends on is gamma times b. Okay. So now what you can do is you can actually tune your selection. So you could select just this slice here, for example, by looking only at the frequency that corresponds to that magnetic field. That allows you to basically to pick a slice. And then I'm not going to describe it in detail, but you can imagine that in the other dimensions, to get x and y, you can do the same kind of thing, like putting a gradient across the lateral direction of the patient or the anterior posterior direction, and using that to kind of raster scan across that space. This is basically how MRI images are formed. So now I'm going to try to explain pulse sequences. I'm going to need to draw this coordinate system here. The field, you can acquire it in Z, X, or Y. And you can measure the field in all those directions. Here's the MZ component, and it decays over time. Remember, we saw those magnets relaxing back up to the Z-axis. This is called the spin lattice relaxation, and here are some values for a tissue. And so we'll relax up at different rates depending on what kind of tissue you are in. Now, actually the way you form images is you let it relax, and then you actually flip it back down to 0, let it sit there for a little while, steady state, and then you let it relax again, and then flip it again. So it's kind of this repetitive flipping of the spins in the tissue. And you can control this, and you can control the repetition rate. And this length here is called TR, the time for repetition. And that's important for T1 imaging because you can control that, and that will give you different weighting for different tissue types. So let me show you how that plays out. Here are 3 curves for fat, brain, and CSF. And the MZ component relaxes at different rates for these different tissues. By setting the TR, you can set the value to be at a particular point in this curve. A short TR is going to be more towards the left, and it's going to enhance differences between tissues with different T1. So a short TR image is going to be T1 weighted, and you would have CSF being dark in an image like that. The signal is low. So far, I've spent most of my time talking about the Z component, but I'm going to switch gears now and talk about this Y component. So to do that, let me draw these little nuclei again. They're oriented in this direction along Z. I'm going to draw a bunch of them now. It's not just one nuclei, of course, it's many. So we're orienting them all this way. Then we turn on an RF field for some time. As we turn on that field, they get flipped down. And if you leave it on for a certain amount of time, they'll flip sideways. So they're all exactly pointed in this direction. And when they're all pointed that way, at that point, you turn the magnetic field off and you leave it off for a while. This is called a 90-degree flip because it flips the spins 90 degrees, 90-degree pulse. Okay, so now let's look at this magnetic field from the top down. All these fields are aligned along the y-axis, so you get some my vector, net magnetization in that direction, adding these vectors all up in a vector sum. And then these precess around the magnetic field with that frequency that we talked about at the beginning, right? Now you wait some time, and sometime later, some of the spins are naturally going a little faster and some are going a little slower. So they sort of spread out. When you do a vector sum of these together, the my is shorter, right? Because they're not all pointing in the same direction. So basically smaller my over time. And now what we do is we flip the spins again. And this time I'm actually going to leave the pulse on longer, twice as long actually. And what happens is you flip the spins all the way around. This first one gets flipped over here. This last one gets flipped over here. Okay, and they continue to precess. Okay, now interestingly, this fast one, or sorry, this one that was fast is over here, and the one that is slow is over here. And so the fast one is catching up with the slow one. At this point, I shut the field off and let it go. Yeah. After this 180-degree pulse. Okay, and now the fast spin is catching up with the slow spin, and after some time, these spins all now align again with each other in the same direction and give another vector sum that gives you a large my again. Okay, makes sense? So this is called an echo, spin echo actually. And you can control when the echo comes. You wait a certain amount of time. Here's the start of this pulse sequence, and here's where the echo is, and that's the TE, the time to echo, which you can control by setting these 90 and 180-degree pulses. And you measure it in your coil, you don't see any signal, and when you get out here where the echo is, bam, you see a signal in your coil. And you can measure the height of that signal, and that tells you what the my magnitude is of the spins in that direction. So here it is, a curve of my. It's decaying over time as these spins relax. The decay constant is T2 star. You can probe different points in this curve by changing the echo time. And so here's what you get. Here's CSF curve and a brain curve, brain parenchyma, and you'll see the my decaying differently. You change the TE value to probe different points along this curve. Higher contrast at longer times, right, between the two tissues. So long TE is a T2 weighted image. And you'll see that in these images, the CSF signal is bright because the signal is large. All right, now that we have a little bit of a grasp on pulse sequences, let's see how this plays out in terms of images. Here's an example of a T1 image and a T2 weighted image, and you'll see that they're quite different. The differences are due to the different TE and TR settings that are used to acquire these settings. Here are the values. So you'll see that the T1 weighted image has a short TR, right? 500 something milliseconds, whereas the T2 weighted image has the long TE, 100 plus milliseconds. So if you look at the fluid compartments, like CSF, cerebrospinal fluid, it appears bright on the T2 weighted image because of the long TE, and dark in the T1 image because of the short TE. Also, on the T1 image, because of the short TR, there's extra enhancement between, let's say, fat versus tumor versus brain parenchyma versus fluid, and so on. And that's what you see. Now, one thing to note here about the T1 weighted image is that it's acquired with contrast enhancement. That's gadolinium that's introduced IV into the patient, and it shows up in the vasculature. It changes the spin lattice relaxation rate at a local level, and it results in a contrast enhancement where that gadolinium is present. So you'll see a bright signal in the vasculature here, for example. You also see that because of the leaky vasculature in the tumor, the gadolinium leaks in, and you'll see a contrast enhancement around the tumor areas. So let me talk about another sequence here, which is the T2 flare. This stands for fluid attenuated inversion recovery. In this image, you'll see it's clearly T2 weighted, right? Because of the long TE here, right? But it's a little different. The CSF and fluid is not bright on this image, but yet it's T2 weighted. So how does this work? I think we can understand this sequence relatively easily, so let me kind of sketch it out. So before we had the magnetization along the Z direction increasing with time, and this is for CSF, let's say. In this sequence, what we're going to do is first align the MZ in one direction, then flip it to the opposite side, and then let it decay. Okay, so you apply a pulse, flip it, and then let it decay. This is for CSF. The curve for brain, of course, decays more quickly because of that T1 relaxation. So this is the curve that you get. Now, if I start this sequence here at this time, instead of starting it at 0, then what I'll see is that the signal in the brain is quite high, but the signal in the CSF is quite low. So I can essentially null out the signal that I want to null out. And I pick my start time to be just right so that the signal from my tissue of interest is nulled out. So now you can understand this flare image, T2 weighted flare image, and why it looks like this. What it's used for clinically in this GBM case is to image the tumor, and in particular, it's thought to trace the tumor infiltrates into the brain parenchyma and give you some assessment of that. All right, now I'd like to shift gears a little bit and talk about distortion and artifacts in MRI, and this is particularly important in the context of radiation oncology, where we need accurate geometric definitions. So to explain this, let me go back to this cartoon, and I think if you understand this, you'll understand really the source of all these distortions and artifacts. Remember that as you change the magnetic field just a little bit, you can select a certain position in the patient, right? And that because that changes the frequency that the spins are processing at. So changing the magnetic field is equivalent to moving a pixel in space. So if you understand that, you'll understand these distortions. Here's an example of how you might get such magnetic field distortions. Here's the magnet that the patient's in, and you want to have a completely uniform field through the patient, but it's not completely uniform. Like here around the edges, the field bows out, and you get different field strengths, like in these different positions. So that, because the B field isn't totally uniform, will induce some distortions. So you can measure that in various ways. Here's a phantom that you can use. It has grids, and you put it in the scanner like this, and then you can make a measurement. And here you'll see an example of the distortion that can happen if you look around the edges. That's because of the inhomogeneity in the B field. There are many various such phantoms available. Here's one that's anthropomorphic. It's like a head, and here's a CT scan of it, and then you can do an MR scan. You can put different grids inside and so on. Here's another type of distortion that can happen, which is the gradient distortion. And you'll remember I told you when you're imaging, you can have a gradient across the image, let's say left to right in this case. And so the magnetic field at one side is higher than the other, so the spins will be at a different frequency. And by doing that, you can figure out where they are in space. Well, if you get that gradient wrong, then the image is not right in that dimension. So in this case, the gradient from left to right is not correct, and the image looks squished in that dimension. Here's another type of artifact called the susceptibility artifact. So magnetic susceptibility indicates the how much magnetization there is in a material if you put it inside of a magnetic field. So if I put something that's, say, paramagnetic in a field, it can itself become magnetized and distort the field around it. Okay, so that can affect where pixels are placed and distort them in the same way as we saw before. And so here's what that would look like. The magnetic field on the left is what it should look like. It's uniform, but then you put something in the field that distorts the field around it and causes artifacts in the vicinity. So an example might be, let's say, an earring that's paramagnetic that you can't or didn't take out, or a belt buckle, or sometimes some hardware that's in the patient, depending on what it's made of. Again, not every metal is paramagnetic, so not every metal distorts. So there are many artifacts in MRI. The last one I'm going to talk about is the chemical shift artifact. And this is illustrated by this interesting experiment that these authors did. These are MR images, spin echo images of an egg. On the right, you can see the yolk inside the egg, the black part, that's hypointense. And then on the left is a hard-boiled egg. And then what you'll see is that there's a sort of artifact in the edge of the egg in the frequency encoding direction. That's the direction where there's a gradient to the magnetic field, which gives you the spatial information. And what you'll see is that there's sort of a shift of the signal right near the edge of the interface where these two materials meet. Okay, and that's because the local magnetic field is slightly different because the chemical composition is slightly different there. And the local magnetic field that comes from the electrons in these compounds is slightly different, and so it shifts the frequency just a little bit right at the interface, and that shifts the position of the image just a little bit, the chemical shift artifact. Okay, that was intense, but now you understand a little bit more about MRI. And you can go back and review this video and try to, redigest it a little more. It takes time, I think, to really understand this. I'm going to leave you with a few references if you want some more reading. Obviously, there are many of them to look at. And then in the next videos, we're going to move on to other imaging modalities and try to hit at least briefly on all the different imaging techniques that are important in the radiation therapy context. Thanks.